I'm going to talk about workload performance comparisons, and what we're going to do here is we're going to look at it in 3 parts. First, we're going to talk about 3 different kinds of workloads we're going to look at, and then we're going to, in the second part, compare performance on an NVMe SSD and a Linux NVDIMM block I/O device, and then an NVDIMM running DAX. And then in the third part, we're going to limit the scope to just the NVDIMM memmap and fool around with some flush settings to see the impact on performance and the trade-offs with persistence. Okay? So, first of all, for the workloads, we're going to take a look at a random 4K write as a standard benchmark workload. Everybody's familiar with that. We're going to look at the industry standard, quote unquote, SQL Server workload, which is often a random 8K 6535 rewrite mix. And then we're going to look at a real world SQL workload. And it's really hard to say real world, so we sometimes use RW. But in any case, the real world workload was captured on a retail web portal over 24 hours, and the IOs that were captured were synthesized into a replay script. And you can see more details about that real-world workload on the SSSI and the testmyworkload.com website as demo number 3. So there's a lot of different stuff about real-world workloads, but it's outside the scope of this talk. Okay? So what do we mean when we say a random 4K benchmark? Basically, it's a single I/O stream that's just run monotonically. We usually keep the queue depth and thread count fixed, and it just runs across. So in this case, what you're seeing here, all the red are the random 4K writes. For each I/O command, everything is a random 4K write. You can see the I/O count at the top of the red zone. You can see the blue IOPS, and the orange line is the queue depth, and the queue depth here is 128. So it's a pretty simple test. Just set the queue depth at 128, run random 4K writes, wait. Like a cooking show, 20 minutes later, you can see the results. Well, what you will notice here is that this is on an NVMe SSD device. So the performance starts out on that FOB plateau on the left, where you have heightened performance, and then it decreases over time, and then you get a steady state at the end. And so that's the classical NAND flash steady state performance slope. This next case is another synthetic workload. This is that random 8K 6535 read-write mix. So in this case, it's just like the random 4K, except 2 things. Instead of a single stream, random 4K writes, now we have 2. Random 8K reads and random 8K writes in a ratio of 65-35. So when you see the streams there, you'll see that the green and the red represent the reads and writes, but all of those I/O streams going across are random 8K. You can see the orange line in this particular test. We're changing the queue depth from 1 to 1,000. So we march from 1,000 all the way down to 1. And then we look at the performance at the different OIO ranges to see where the performance peaks and what the range of performance is over the queue depths. So in this kind of test, you can see where the I/O saturation point is and where the response time saturation exists. And then finally, this is a depiction of the real-world workload for the SQL Server workload. So you notice the difference here is for the I/O streams, instead of having 1 or 2 I/O streams, we have many. The actual observed workload had 1,000 I/O streams, but 6 or 9 of them comprised 70 to 90% of the workload. So in this case, we extracted or filtered out all the SQL Server identified I/Os and looked at those. And of those, you can see there's 6 dominant I/O streams that occur over the 24 hours. But for each step of that capture, they change in their nature. So that spike on the left, that orange spike, is a 2 a.m. backup and a 64K read writes. Whereas when you look at the opening, bootstorm, and other areas in here, you can see that the I/O streams start changing to sequential half-K writes and 64K reads and so forth. So while you can look at the workload over a given period, in this case 24 hours, and say, I had 30% random 64K reads or 29% sequential half-K writes, it depends on where along this time you see it, because those will change. So the average over time is 30% or 29%. But if you do a replay test, you actually replay the order of the combinations of I/O streams that you see. Simply put, that means that so far into the test, you'll see only random 64K read-write, and then later on you'll see sequential half-Ks and so forth. The other thing that changes is the queue depth. So we have a dynamically changing queue depth, and that just reflects the server throttling of the storage performance. simple way of saying if nobody's using it and I have one user, I have a low demand intensity, I'll have very fast response times but low IOs. On the other hand, during a morning boot storm, I might have 1,000 guys accessing the server, so the performance goes down and the response times go up. Okay, so we have a one-stream workload, a two-stream workload, and a workload where we have 6 streams that vary constantly over the duration of the script. Okay, that's section 1. Okay, here we're going to look at testing the NVMe SSD, the NVDIMM as a Linux block I/O device, and then the NVDIMM as a DAX file system memmap. We're going to run 4 tests. Test A is the random 4K write, single I/O stream, fixed queue depth. The second one is the 2 I/O stream with the queue depth varied over the course, so you see the performance of a range from 1 to 1,000 users. And then the third case will be that real-world workload with those 6 I/O streams. In this case, we're just going to run a fixed combination of those I/O streams that you saw up here. Let's go back. So these 6 streams will occur for every step of the test. So every step will show 30%, 29%, 16%, 14%, 5%, and 4%. And then in the last test, we're going to actually replay them in the order that they occurred. So instead of being a fixed combination of 6 I/O streams for every I/O command will replay what was observed during the capture. So the results. What you can see here is NVDIMM is on the top. The block I/O, I'm sorry, I misspoke. The NVMe SSD is at the top. The NVDIMM block I/O is second. And the NVDIMM memmap is third. That order will maintain through all the slides. The workload is just represented here, single stream, random 4K 4 writes. Yes. Okay. I'll look down then. So on the left, you will see which device it is. So for all of the slides, the NVMe SSD is first, the NVDIMM block I/O is second, and the NVDIMM memmap is third. In this segment, we're using multiple cores, multiple threads, and multiple queue depths. From that variation from 1 to 1,000 users, we picked out the combination that showed the best performance for each of the devices. So for the NVMe SSD, it was at thread count 2, queue depth 16. We had 27,848 IOPS and 1,150 microseconds for average response time and 1.5 million for the 5 nines response time. That's a quality of service response time, 99.99%. For the NVDIMM block device, the optimal setting was thread 8 Q1, and you saw 2.9 million IOPS and 2.7 microseconds average response time. And you saw for the NVDIMM DAX memmap, substantially the same IOPS, 2.8 million, but you notice that the response times are faster, 1/4 of the block I/O, so 0.7 microseconds to 2.7. Looking at the 5 nines number, it's 21 to 19, so they kind of flatten out when you get to the edge. Following each of these box tables, there's a plot that shows it. So this is just a graphic visualization of what I went through. On the left side is the NVDIMM block I/O device. You can see 2.9 million IOPS on the white box on the top, and 2.7 and 21 for the average and 5 nines response time. On the right-hand side is the NVDIMM memmap. And over here you see 2.8 million IOPS at the top in the white box. And you see a 0.7 average response time and a 29 microsecond 5 nines. And then in the middle is our NVMe SSD friend, 27,000 and 1,100 microseconds for the average response time. Again, you can download this and look at it in detail, but the basic theme here is that you're going to see the NVMe SSD orders of magnitude slower than the NVDIMM devices, as well as much slower for response times. So now we shift to the 8K, random 8K 6535 rewrite mix. Again, they're in the same order. What you'll notice is, again, the NVMe SSD is 38,000 IOPS compared to 2.1 million and 1.9 million for the NVDIMM block I/O and the NVDIMM DAX. Again, you see the same progression of response times. So focusing down here on the NVDIMM, it's 8 microseconds for the block I/O, but it goes down to 3.1 microseconds for the DAX memmap. And similar for the 5 nines. Okay, and then the next one, we're going to look at the 6 IO stream workload. Oh, here's the graph for that previous one. So again, you can see IOPS on the top on that orange line, and then the bars are response times. Okay, for the third case, we're looking at the synthetic real-world SQL workload. This is those 6 IO streams, but we're going to apply the 6 IO streams in a fixed combination for every IO command. Okay, they're not going to vary over time, so you're going to get the same 6 IO streams for every step. In this case, you see the same relationship between NVMe SSD and the NVDIMM, so 22,000 to 750,000. But you also notice that that 750,000 range number for both the block IO and the map is much lower than the previous slides where you had 2 million and 1.9 million. Accordingly, the response times, you can see you're at 2,800 microseconds for the NVMe SSD device, but both the NVDIMM devices are at 11 microseconds for average response time and roughly 50 microseconds. So the performance here between the NVDIMM block IO and the NVDIMM map is roughly the same, but remember here we have a multi-core, multi-thread environment. We will look in part 3 at a single core T1Q1 test of map, and we will see some difference in performance when you look at different flush commands. And here's the graph for this. And the fourth case here is using that real-world workload, but now we're going to replay it just as the capture showed us. So you might recall there was a 2 a.m. backup where there was a spike of 64K read-writes at 2 a.m. and then low activity during the early morning hours, then morning boot storm. So you're seeing for every step of the test script a different combination of IO streams and a different queue depth. Under this case, you can see that the performance for the NVMe device went down from the 27,000, 38,000 range for the previous test to 7,000 IOPS. And then you can see that the NVDIMM block IO device is 750,000, while the NVDIMM map is almost 2 million. So there's a big difference here, 1.9 million to 749,000, and you can see 1 mic to 15 mics for the average response time. Why is it different? I don't know. We just took the test. There's different mix of 6 queue depths with different block sizes. But note that in this case, you do see a difference based on the workload. Okay, so that's the first section. The second section of testing now, we're going to step away from the NVDIMM device, and we're going to look at it only a DAX map of the NVDIMM device. And in this case, we are going to, so on this last test, we did the real-world workload and replayed each step. You can see that when you look at the performance over time, you can see how the IOs, okay, sorry. Speak into the mic. Move the mic to the right-hand side of your mouth. Are you filming this too? This is going to be funny. Okay, so here is the replay of the sequence of different IO streams that you see in the real-world workload. So remember, we had a single 64K read-write around 2 a.m., morning boot of a bunch of different IO streams. You can see that the performance changes over time. So while you look at the average number in the previous slide of 750,000 to 1.9 million, what actually happens is for much of the time you're at roughly 900,000 for the block IO and maybe 1.3 million for the map. So this is the challenge of looking at real-world workloads and trying to pick a single number. You've got performance that's changing over time, and you can see graphically, what's going on, but when I want a quick reference number, I get 750,000 to 1.9. Oh, the 1.9 must be much better. Well, yeah, but if we look at over here, there's a crossover where the blue is better than the orange. So just beware when you're looking at a replay test. You want to know what portion of the replay you're looking at and what the workload composition is at that time. Okay, so that was part 3. Now we're going to look at a single core situation. CPU core is single. We're going to look at map, memcopy, and memsync. So in the first case, there'll be no flushes. In the second case, there'll be non-temporal writes. In the third case, we'll be doing msync, software writes through. And I forgot to mention the test setup before, but on every chart here, you'll see at the bottom this tiny, tiny script. You can't see it, but it says test platform with a Supermicro something something. I have to put my glasses on. Supermicro X11 DRI with 16 gigabytes of DDR4, 2133 megahertz RDIMM RAM, an Intel Xeon 8160, 2.1 gigahertz, 24-core CPU, and a single 16 gigabyte DDR4 JEDEC NVDIMM-N device. So, and then for the software, it's either going to be Linux, Ubuntu, or DAX file system, and the test software is a Calypso, CTS, bunch of numbers. We intended originally to run this test with a single DIMM device and then run it with 4 DIMMs interleaved, but we didn't have time to do that. So all the questions you're going to ask about that, you can just hold. We'll come back with an updated presentation that shows that. All right, so the numbers, you can see that on the, this is going to recur for all of them. The NVDIMM MEMMAP with no flush is the fastest performance, but it had the slowest response times, okay? In the second case where you have non-temporal writes, the cost of getting the added persistence is a drop in the IOPS and an increase in the response times. And in the case where you have explicit flushes for every IO command, of course, that's going to have the highest cost to performance, but the best in terms of persistence. So here you see 1.7, 770, 403. Okay, this is for the random 4K write workload. The next one, I'm going to bypass this for the interest of time, is the random 8K 6535, 2 IO streams. And you see the same relationship where you have 900, 750, and 4, but it's a narrower range. Okay, so for this workload, because it's reads in there and they're 8K, perhaps, so you can see though that the basic performance is the same, where my IOPS are higher, but my response times are also lowest, and then they increase as you go down. So I go from 900 to 460, I go from 0.8 to 2. Okay, and then the third case we're looking at here, this is the real-world workload, applying the fixed IO command for every step. We didn't do the replay here, single core, and you can see in here it flattens out even more. So you have 400 and it degrades to 350, but I might argue that that's not a lot of degradation, but you can see also the response times are substantially the same. Okay? So, conclusions. You can read these, but we can see that workload definition has an impact on performance comparisons. Kind of depends on what you're testing. That seems self-evident, but when you start to look at real-world workloads, it becomes more exaggerated. Second point, the NVDIMM block I/O is faster than the NVMe SSD by orders of magnitude. So you saw 27,000 IOPS versus 2.1 million. At the same time, if you look at the NVDIMM block I/O versus the MEMMAP load store without flush, you have substantially equivalent IOPS performance, but the response times, MEMMAP has better response times than block I/O. Okay? And then the last bullet with the sub-bullets talk to using a DAX file MEMMAP with no flushes, with non-temporal writes, and with MSync. And as we saw in the previous slide, the performance is highest when there's no flush. But as you get the most persistence by flushing with every IO command, there is a overhead where you lose some IOPS performance. How's my time? I went 3 minutes over, but there's one question. Lunch or question? Lunch? Question. Okay, question. Yes. I think you do need the mic because they're recording this. And my name's Dan. In case you have any critical comments, my name's Dan. I just flew in. Yes.
On your page 14, where you showed the 5 nines data, there's kind of very large number for the 5 nines for the memory mapped NVDIMM. Is that some kind of typo, or indeed this happened in reality that you had 3 milliseconds 5 nines for the memory mapped NVDIMM?
That can be real, because it could be like a sequential 64K write that occurred. I don't know. I'd have to look at the data more closely.
So
but it's not a typo.
Not
it's not a typo. It is the number.
Yeah.
Again, as I said at the beginning, I don't know the whys yet. I just know the whats.
And then just for clarification purposes, the NVMe SSD used is a NAND based, right?
Yes.
It seems from the numbers. All right.
Yes.
All right. Then
400 gigabyte device.
It would be better to use the Optane NVMe SSD for the more fair comparison.
It may be that device.
Yeah.
I can't tell you.
Okay. Well, I think from the numbers.
I'm the president's psychiatrist. I can't tell you anything. Any other questions?
Yeah,
One last question. Oh, Tom.
Sorry, I have to challenge your third conclusion.
Yes.
And that is that the mapped mode is substantially the same as the block mode. The fact that you saw no advantage in IOPS in mapped mode tells me that you have a bandwidth problem on your memory bus. You know, there's some bottleneck. Mapped mode will definitely be faster directly on the memory bus than block mode because you're not transitioning to the OS, you're not sending
Yes.
IO requests down the stack.
But in that comparison, we had a multi-core for
Yeah, I know. Well, that makes it even worse because now every core is
Right,
banging the data
right.
to the same device.
Right, so I agree with you.
I strongly suggest that you do the multiple DIM test before you draw that third conclusion.
Okay. Point well taken.
You better do it.
All right, so what really happened was last Wednesday, we had a conference call with Doug Voigt and Jim and Tom, and they said, why don't you do these new tests? So we ran these tests over the weekend, and on Tuesday, we're trying to get the data together. And last night, I was with Arthur and Stuart at 8 o'clock in the lab going, what are we going to do for tomorrow? So we didn't have time to really scrub it and go through, but we'll take these comments and run the data with the interleaved and try and get more accurate resolution on some of these.
Steaming hot data. Great.
Nothing new, you've all heard it before. And the demo should fail, as all demos do, so go back and look. All right, who wants lunch? Thank you.